Assalamualaikum. Hi and a very good afternoon, ladies and gentlemen. Honorable Committee of Konsep 2024. I am Faruza. Will be presenting on the review paper with the title of Enhancing Agriculture Productivity through Iron Oxide Nanoparticle Priming, Opportunities, Challenge and Surface Modification Strategies. Malaysian agriculture sector. What is the problem? Did you know that agriculture today is facing several issues to sustain the food production? Malaysia currently occupies the 41st position on the Global Food Security Index, and by 2050, it is predicted that the global population will reach 9 to 10 billion, requiring 25 to 70% increase in food production. Afraid not, research and technologies have demonstrated that nanopriming is one of the keys to improve the performance of crop. It modulates biochemical pathway and the balance between reactive oxygen species and plant growth hormone, resulting in the enhancement of the morphological, physiological, and post-harvest physiology of product. Specifically, the iron oxide nanoparticles have been recognized for their inherent properties such as superparamagnetic, extensive surface area, and ease of separation that amplify the seed germination and crop growth. However, concerns arise regarding this nanoparticle in seed priming as it tends to aggregate into the weed forces. It can easily lose their colloidal stability and agglomerate to lower their surface energy. Due to the expanded size and uneven sediment concentration, these may cause phytotoxic impact in plants and reduce the plant performance. Accordingly, surface modification is required to stabilize this magnetic nanoparticle. Hence, as far as is known, the colloidal stability of nanoparticle can be improved by having the surface functionalization due to the increases in zeta potential. Along with that, the seed priming is in line with SDG 2030 number 2, which is related to the agricultural production. Hence, this review focus on assessing the suitable material to reduce the agglomeration issue of iron oxide nanoparticle based on its characteristics, specifically the zeta potential. So, nanoparticles are frequently stabilized by forming a dispersion layer around the external surface. The stabilization of suspension with high nanoparticle concentration depends on the creation of egg layer at the proper thickness, while narrow egg layer cause particle to aggregate. Thick egg layers produce an enormous restricted volume around the particle. Theoretically, the zeta potential of nanoparticle on their surface shows that the particles are persistent. Higher negative or positive zeta potential, the nanoparticles tend to resist to one another and reduce the aggregation. In general, it is anticipated that the zeta potential value beyond the range of 13 millivolt has enough repulsive forces to improve the physiological stability. According to the research finding, the iron oxide nanoparticle exhibit a poor stability and a tendency to agglomerate with an average hydrodynamic particle size of more than 300 nanometers and the lower zeta potential for about 14 millivolts. Thus, the main method to prevent the agglomeration are particle coating with a capping agent to separate the particles using the electrostatic repellents. There are few studies that have been conducted to reduce the agglomeration of nanoparticles. One of them is by using polyvinyl pyrrolidine PVP that brings down the average particle size of about 800 nanometer to about 200 nanometer with a zeta potential of about 40 millivolt. PVP is a capping agent that works through the steric effect dependent on its hydrophobic strength to stop the aggregation. It inhibits the formation of iron oxide crystal and controls oxidation. Due to its non-toxicity, biodegradability, biocompatibility, and temperature resistant, PVP is one of the most widely utilized polymeric materials to encase the iron oxide nanoparticle. It also acts as a carrier for the nanoparticle in medication delivery system and iron-containing nanocomposite. Then, the surface functionalization using chitosan. It is a bioactive substance obtained from the crab shell and shrimp. Besides, chitosan is one of the most finest possible biopolymers, and it is not only promotes growth and raise crop yields, but also lessen the negative impact of saline condition that successfully boost plant physiological characteristic and lengthens the lifespan of the post-harvest product like fruit. Then, the electrostatic repulsion of chitosan further enhanced the stabilization effect. The combination of both steric repulsion and electrostatic repulsion yields electrosteric stabilization effect. With this stability, higher energy barrier can be formed to prevent the agglomeration. As far as is known, by coating the nanoparticle with chitosan by co-precipitation method, the agglomeration during iron particles can be minimized during the synthesis process. Using the chitosan to modify the surface of iron oxide nanoparticle is one of the methods that have been in the current investigation. According to the previous study, the average particle size and zeta potential of chitosan-coated iron oxide nanoparticle were about 300 nanometer and a very high zeta potential value, which is more than 70 millivolt, following the addition of chitosan, demonstrating the improvement in the colloidal stability. Next is by capping with amorphous silica. The nanothin silica shell protects the magnetic cores against the flocculation, agglomeration, and corrosion while maintaining the shape and magnetic properties of iron oxide nanoparticle. In addition to enhance the magnetic nanoparticle stability, the silica covering serves as a scaffold for the attachment of various functional groups, such as silica-coated iron oxide nanoparticle that can be made using sol gel technique. In terms of its zeta potential, the silica-coated iron oxide nanoparticle with the smallest particle size, which is about 200 nanometer, and moderate colloidal stability for about 30 millivolt. This shows that silica-coated iron oxide nanoparticle has a moderate stability that reduces the agglomeration issue compared to the uncoated iron oxide nanoparticle as discussed earlier. Therefore, nanomaterial-based products are being offered to revolutionize contemporary agriculture practice. These materials are able to meet the rising demand because of their high reactivity, high surface area to volume ratio, and new physical-chemical features. It's still a very recent field to study this nanotechnology for the seed treatment. However, the aggregation of the particle in biological and physiological condition present a problem when using only iron oxide in seed priming. The introduction of less tough seed polymer that can hold into the iron oxide nanoparticle in lower cluster size over a long term can be used to surface functionalized nanoparticle. Thus, to conclude this review paper, we can, as far as known, reduce the agglomeration of iron particle during the manufacturing process when surface modification of nanoparticle is applied by using the chitosan. Despite all the prior research, there is still lack information regarding the impact of different molecular weight of the chitosan coated to the nanoparticle on crude output. Hence, that's all from me. Thank you so much.